All right, shall we get started? Lesia? Great. Yeah. Hello, everyone. Welcome to the Early Career Researchers webinar series presented by Informs JP. This series seeks to increase the visibility of research conducted by junior faculty and senior PhD students within the fields of OR and MS. Please follow our Twitter and LinkedIn accounts for subsequent webinars, and please let us know if you're interested to present. Today, we are happy to present two talks. First by Dr. Lesia Mitridati. Lesia is an assistant professor in the Department of Wind and Energy Systems at Technical University of Denmark. Prior to this role, she was a postdoctoral scholar at Georgia Tech and ETH Zurich. Her research interests are at the intersection between optimization, game theory, machine learning, and their applications to energy markets and power systems. Lesia, we are very happy to welcome you here. The floor is yours.
Thank you. Let me share my screen. All right. Yeah, thank you for inviting me. So today I wanted to present some of the work I did that I studied at Georgia Tech and continued at ETH on the cost of privacy for the coordination of energy markets. Okay, so the motivation for this work was to coordinate the operation of multi-energy systems, and specifically to harness the flexibility that is at the interface between the systems. This can be achieved by coordinating the independent and sequential markets that currently exist for these systems. However, this requires the exchange of some sensitive data between the different market operators. So the contribution of this work was to design an algorithm that facilitates the exchange of high quality sensitive data between the energy market operators to enable a near optimal coordination between them. Okay. Specifically, so the motivating example that we looked at first was heat and electricity markets. So why is it important to coordinate these two markets, and what can be achieved by coordinating them? The current way heat and electricity markets are operating in Nordic countries such as Denmark is sequential and independent. So in the day ahead, first the heat market is cleared. CHPs, heat pumps submit bids in this market. The market operator minimizes the heat production costs subject to constraints on the heat production and system operation. Once the heat dispatch is decided, the CHPs and heat pumps then participate in the day-ahead electricity market, and this market also minimizing the electricity production costs subject to its own constraint on electricity production system operation. There's two notable interactions between these systems. The first one is that the constraints on electricity production in the electricity market are highly dependent on the heat dispatch in the heat market. And that's because of the feasible operating region of heat pumps of CHPs. So if you look below this figure, you can see the feasible operating region for heat and electricity of a combined heat and power plant, CHP. And you can see that depending on the heat production that is decided, the electricity production is constrained. The second interaction this time is in the heat market is that the heat production cost of CHPs and heat pumps depends actually on the electricity prices. So if you look at these curves, you can see the marginal heat production cost of CHPs and heat pumps based on different electricity prices. So this basically represents an opportunity cost for CHPs to not sell more electricity, and for heat pumps, it represents the cost of purchasing this electricity to produce heat. So this type of interaction between two sequential players is actually very representative of a classic Stackable game. So a Stackable game is a game between two sequential players, where the first player, called the leader, optimizes its own objective, and its objective value is impacted by the reaction of the follower. And the follower's problem, the follower tries to also optimize its own objective once the leader has decided on its action, but its reaction and feasible space are impacted by the action of the leader. So for the leader, in order to achieve better optimization and coordination with the follower, they need to anticipate on the reaction of the follower. So how can the leader actually anticipate these interactions and model them? So if we look at the follower and the leader's problem currently as two sequential and independent optimization problems, we can formulate them in as a standard optimization problem, each one of them. And we can see we model the objective cost of the leader as dependent on the dual variables of the follower's problem, and we model the constraint of the follower's problem as dependent on the primal decision of the leader. Currently, in those two sequential problems, the leader's actions and followers' reaction are treated as exogenous parameters in their optimization problems. In order for the leader to anticipate the reaction of the follower, they want to treat their reaction as an endogenous variable in their problem. And this can be modeled as a hierarchical optimization problem. So in this Stackable coordination mechanism, we define hierarchical optimization problem for the leader's problem, where they try to optimize their own objective cost subject to their own constraint, and model the reaction of the follower, so their dual variables, as an embedded optimization problem modeled as a constraint of their problem. So this way they can anticipate the interaction with the follower and optimize their own decisions. Once the leader has decided their actions, then this is sent to the follower, who then solves its own optimization problem. So this Stackable coordination mechanism we've applied to the coordination of heat and electricity markets. And just to illustrate the benefits of this approach, we've compared it to the current decoupled approach, where the electricity prices are treated as exogenous parameters in the heat market, and to an integrated approach that minimizes the total operating cost of the system subject to all the constraints. This would be an ideal benchmark, whereas the decoupled approach is the current approach. And then the electricity aware approach is our coordination approach, which is still sequential. So we compare these three models. We tested this on the IEEE 24 bus system connected to two isolated district heating systems. And for different values of wind penetration, we conducted simulation over 1 year. So at the interface between those two systems, we have two CHPs and heat pumps. So that's the flexibility that we have and can exploit. So if we compare the operating cost in electricity and heat systems, what we observe is that the electricity-aware approach reduces the operating cost in both systems compared to the sequential approach. So this table represents the heat, electricity, and total cost difference in percentage of the integrated market cost, which is the ideal benchmark. So we can see that the electricity-aware approach achieves for all the values of wind production, lower cost in electricity and heat systems. And this is because it's able to better utilize those flexible resources and achieve a better coordination between the two markets. So there is benefit to doing this coordination, and there could be great economic advantages. But if we look at how the leader modeled this coordination, we see that in its own optimization problem, in the lower level, it needs to know the data of the follower in order to model its optimization problem. And some of these data might be private and sensitive. So the follower might not be willing to share this data. In this current setup, we assume that the follower was first sharing exactly its data with the leader, and then the leader was solving its optimization problem, knowing the private data of the follower. but in order to protect privacy on the follower's data, and especially time series of loads, for example, in the electricity market, the second step of this work was to develop an algorithm that would protect this sensitive data before sharing it with the leader. So this is what we called the privacy-preserving stackable mechanism, where we add one privacy step before solving this stackable game mechanism between the leader and follower. Once we've done that, the leader solves its own problem, this time using the privacy-preserving data of the follower. So let's look at how we designed this privacy-preserving mechanism. The privacy goal of this privacy-preserving mechanism was defined using differential privacy framework. So differential privacy basically tries to protect, in this case, time series, and it tries to protect variation between two time series up to a certain indistinguishability level. So that means that an attacker that would observe the outcome of the mechanism, this randomized mechanism, for two time series that are close enough within this indistinguishability range, and over a time window, would not be able to tell which data is which with a high probability. So this is the privacy goal that we're trying to achieve. And we know for a fact that the Laplace mechanism of a scale W times alpha achieves W differential privacy over, so with alpha indistinguishability and over a time horizon of W time steps. So if we apply Laplace noise to the original data, then an attacker observing this original data cannot infer it with a high probability. So the first step of our WPPSM is to add privacy by obfuscating the original sensitive data by adding a Laplace noise to this data. And this is, this is the first step using the Laplace mechanism. The main challenge is that since we need to scale this noise added based on the level of indistinguishability, but also the number of time steps that we want to protect, this is adding a lot of noise to the data. And this highly perturbed data may be infeasible for the follower's problem, or it may yield solutions that are far from optimality for the leader and the follower. So we have a huge gap in optimality in this case. So to resolve this issue, what we've done is to add a second step to this privacy preserving mechanism, which is a fidelity recovering phase. In this phase, we restore fidelity with respect to the original solution of the Stackable game. So we try to find a new perturbed data that reduces the suboptimality of the leader and followers problem after the WPPSM. So more precisely, the fidelity goal is to bound the loss of optimality for the leader and the follower with respect to their original optimal costs before the application of the privacy preserving mechanism. And this optimality loss we define as the cost of privacy, and it's the difference between the cost, the optimal cost of the leader and the follower before and after we applied the privacy preserving mechanism. So our goal is to try to bound this cost of privacy for both leader and follower. And we can redefine this cost of privacy by defining a feasible space of all the data such that the cost of privacy is bounded. So this is a non-convex set, and we cannot guarantee once we've perturbed the original data. So the original data is in this set, but we cannot guarantee that the Laplace obfuscated data is in this set. So we want to try to enforce fidelity by projecting this perturbed data into this feasible space so that we can ensure that the new data that is privacy preserving also ensures fidelity with respect to the original cost. So this can be done using a hierarchical optimization problem. So the goal of this optimization problem is to find a new optimal data set that is as close as possible to the original Laplace obfuscated one that ensures that the cost of privacy for leader and follower with this data is bounded by some parameter that we need to tune. And these new optimal costs are defined as the optimal cost of the leader with this new and the follower with this new input data. So these two constraints represent two optimization problems. That's why it's a hierarchical optimization problem. So since when the follower needs to solve this optimization problem to redistribute the noise on its data, it does not know the optimization problem of the leader or its parameters. So it cannot directly solve this optimization problem to redistribute its noise. So instead, we use some kind of proxy of the optimal cost of the leader. Since we know that the optimal cost of the leader is directly impacted by the dual variables of the follower, then instead of enforcing these constraints, we enforce constraints on fidelity with respect to the dual variables of the follower's problem. So by doing this and replacing the fidelity constraint on the cost of the leader by fidelity constraints on the dual variables of the follower, we use this as a proxy for reducing the cost of privacy of the leader. And now we can solve this as a bi-level optimization problem and redistribute the noise so that we enforce those two fidelity constraints. The overall, as a summary, this privacy-preserving stackable mechanism achieves the privacy goal of being differentially private. And this is due to the immunity to post-processing of differential privacy. So any transformation done to the data after it's been perturbed does not impact its privacy level. And it also achieves the fidelity goal of bounding the cost of privacy. We can actually derive theoretical bounds on the cost of privacy for the leader and follower after this PPSM has been implemented. So now we have theoretical properties, but we also validated this approach on a small case study. So we used the same 24 bus system and 3-node district heating network. And we simulated their operation over one reference day. And for this reference day, we compared the fidelity of the Laplace mechanism, the naive Laplace mechanism, and our WPPSM approach. And we compared this for different values of privacy levels, so different indistinguishability levels alpha. And what we can see, first of all, when we compare cost of privacy for the leader and the follower for both mechanisms and different alpha values. So as the value of alpha increases, the noise of the Laplace mechanism increases. So for the Laplace mechanism, the cost of privacy greatly increases for the leader. Whereas in the case of our WPPSM mechanism, the cost of privacy for the leader does not increase when we increase the indistinguishability level. So this achieves a good trade-off for the leader between privacy and fidelity. If we look at the follower, actually for both mechanisms, we see that as we add more noise, we actually decrease the cost of privacy. And this, the interpretation intuitively that we have for this result is that adding privacy to the follower's data might reduce the strategic advantage of the leader knowing the data of the follower to optimize its own cost at the detriment of the follower's cost. So, but we can also see that our mechanism also achieves significantly lower cost of privacy compared to the naive Laplace mechanism. Now, we also compared the performance of those two mechanisms under different operating conditions. So does the operating condition of the system, the loads specifically in the heat and electricity system, does that impact the cost of privacy for both mechanisms? So what we did was we applied some uniform factor to the heat and electricity loads. So we compared for loads in the heat system between 40% and 160% of the load in the reference day. And in the electricity system, we looked at loads between 50% and 200% of the electricity load in the reference day. So for those two, for all those possible combination of loads, we compared the cost of privacy in the Laplace mechanism, which is the figure up, and down we compared to the WPPSM. And so what we can see is that for, I think this is for an distribution level of 10, the WPPSM achieves significantly lower cost of privacy compared to the Laplace mechanism for any possible operating conditions. And it achieves several orders of magnitude lower for some of the operating conditions. We observe similar results if we compare the follower's cost of privacy, although overall it's lower orders of magnitudes. So this tells us that this is robust for different operating conditions, and also this allows us actually to identify different operating conditions in heat and electricity systems for which the cost of privacy for the leader and the privacy costs for the follower increase. And this can be helpful if we want to apply privacy only when it matters. So if we want to develop a mechanism that is adaptive over several days, where we adapt the noise that is added based on how sensitive the data is. So how risky is it for the follower to reveal this data? Is there a high possible cost for privacy leakage? And how much does that impact the leader's objective? So for further work, so what we would like to work on is to now, over repeated days and repeated instances of this Laplace mechanism and WPPSM, to try to dynamically adapt the noise based on a certain threshold of the impact of privacy on the leader and follower. And yes, so that's it. Thank you for your attention. And I hope you have some questions later.
Yeah, thank you so much for this great talk. I find it very inspiring. So the audience, if you have any question, feel free to use the Q&A box to raise your questions. We do have time.
I can't see anything.
So maybe they are typing up their questions. So meanwhile, maybe let me ask a question. I feel this is quite interesting. So you described like the leader is actually using the dual optimum solution from the follower to make its own decision. So have you considered this alternative dual optimum solutions? You know, so the lower level problem might have like multiple equivalently optimal dual variables to use. Like so in the model, I assume like, you know, I see that you kind of use this in this optimistic way, right? So if there's an alternative dual optimum solution, then the dual optimum solution must be like helping the leader to solve its own problem. But in reality, do we need to worry about that? You know, in reality, maybe the follower doesn't know that. It just report this, you know, kind of one of this dual optimum solution. So to what extent might that hurt the leader's purpose?
Yes, no, that is correct. So that could happen, and that happens because it's a linear problem. So there are multiple solutions. There could be multiple solutions. So for example, if the CHP bids at the same price as another unit, then we take the optimistic approach and says that the CHP was dispatched, right, in this approach. So yes, we haven't studied how to solve this in a pessimistic manner, and the results that we've presented, though, the numerical results are, so we're solving the electricity market after the heat market has decided. So technically, we don't know if it actually, we don't enforce that it actually picks the optimistic solution. But yes, that is definitely something that we could look into when there are multiple solutions.
Yep, great, thank you.
Thanks.